Hello, my name is Michael Elezen. I am a research engineer in charge of new server cooling technologies for two server sides. My expertise is more specifically on monophasic immersion cooling. And today, my objective will be to share 2 years of work analysis and learnings about monophasic immersion. I will cover the monophasic immersion through 4 pillars: material compatibility, mechanical and thermal, electrical, and software. Two-SI Group is designing and manufacturing high-performance and sustainable servers. Design is done in France. Manufacturing is taking part in France and the United States. At two-SI, we have always been focused on the energy consumption coming out from our servers. It led us to innovate, first on the air cooling solution for our servers, then on all the new cooling technologies to provide more energy-efficient solutions. 2 years ago, we tackled the immersion cooling by rethinking the way to design our two-SI servers. Basically, single-phase immersion cooling consists of immersing servers in a tank filled with non-electrically conductive liquid. The high thermal capacities of these liquids allow them to dissipate heat from the hot spots of the servers. Whether by natural convection or by forced convection, this hot liquid will get in contact with a cold exchanger, which will transfer calories. Then the external water network will evacuate them. For immersion cooling, a dielectric liquid is used. These liquids have specific chemical compatibilities. Obviously, the thermal paste used for air cooling are not compatible with these liquids. The thermal paste will gradually dissolve into the liquid, which may affect the cooling of the CPU or GPU. After several tests, we finally decided to replace these liquids by hydrogen sheets, stable in immersion. Most processors are sealed and do not present any problem while immersing into a dielectric liquid. However, some processors have slots which invite liquid to enter, driving CPU malfunction. The appearance of the problems can vary over time depending on the liquid composition. On the right picture, you have an example of slots issue on a CPU. You must check that the selected processor will match accordingly. When your servers are submerged in a tank, they are connected, meaning that both the network cable and the power cable are connected. It will be key to get chemical compatibility between your cable and your liquid. Some submerged sheets can have a stiffening effect, which can break the protected sheet. You can also have capillary effect, which causes a rise in the liquid along the cable. On the right picture, you can see a network cable which has lost all its flexibility. You also have to pay attention to standard fiber optic. For the majority of them, the liquid can get into the connector and affect the signal long-term speaking. Components usually have labels stuck on them. On contact with the liquid, the glue can be removed and cause peel the label off. Implications are diverse. Tank cleanliness modification, issue to identify components, or warranty implication. To prevent from this, we have to refine two solutions. The first solution, use the plastic-resistant labels to identify your components in your server. Tracking of each component is safe, which is useful when you deploy several Windows servers at once. Second solution is to cover label with transparent epoxy resin. On the right picture, you can see a label covered with epoxy and submerged for several months. When the immersion technology started, component manufacturers did not guarantee their product for immersion. This way, TrueCRSI decided to cover this warranty for its customers. Time is changing now, as we can observe that manufacturers are starting to offer warranty immersion products. Regarding the servers themselves in immersion, the position of the components in an immersed server is directly related to the heat flow. Overall, to optimize cooling, the hottest component will be placed at the bottom of the server, and the coldest will be placed at the top of the server. However, if the technical specifications of the servers do not allow this typical location, a thermal study combined to a test will be carried out to answer the right cooling. The component will be placed to avoid blocking the flow of the liquid and potential hotspots. To do so, the exchanger fins will be oriented into the direction of flow, as shown in these pictures. It is also possible to size the fins according to the type of the liquid used. The aim will be to optimize the heat exchange. The thermal capacities of this type of cooling make it possible to imagine arrangement of components and densification previously impossible with air. Still, to facilitate the flow of the liquid, its input and output from the server, we will keep a space between the surface of the liquid and the top of the server, as well as a space between the bottom of the server and the bottom of the tank. You can see on this graph a comparison between the CPU temperature versus time. We draw a test with several immersed servers in heating, and we cut the cooling of the tank. We observe the rise of the server's temperature. You can see that it takes almost 4 hours for the CPU to rise by 20 degrees Celsius. When we restarted the cooling and the tank's temperature decreased, and the temperature of CPU dropped very quickly. Even if the tank was not full for this test and the time for heating the liquid remained linked to the power of the submerged server, the temperature rise of the liquid is slow because directly linked to the thermal inertia of the liquid. It means that this type of issue happens is leaves time for a technician to intervene and resolve it quickly. Even if the intervention does not take place, as the rise of the temperature is gradual, it will avoid stressing the component too much before they fail. One of our customers experimented such issue. The temperature of the liquid has risen and the servers have failed before they can react. What is interesting is they told us that if they had had such a problem with their air equivalents, they will have changed many components in the following months, with all the costs that this implies. But with their servers submerged, There is no breakdown. The server continued to operate as if nothing had happened. The main reason for this result are the homogeneity of the temperature in immersion and the gradual and slow rise in temperature. And for us, these are precious returns that confirm us in this technology. In immersion, a number of mechanical adjustments have to be done to avoid issues. Fixing suitable for submerged components, some components need to be secure because during immersion they can come out of their location, like non-fixed PCI Express expression card. Use of X-socket screw. This type of screw avoid metal piece during screwing or unscrewing manipulation. This PC could touch other components and create contact failures. Chassis reinforcement for easier extraction. Unlike air chassis, you have to bear the weight of the vertical extraction. And to facilitate manual extraction, you must add handles adapted to this extraction. Electrical components are done for air applications. However, even if most of them work perfectly within dielectric liquid, we need to remember physical properties between air and dielectric liquids are different and could change passive value of components, like the electrical permittivity. It's something we are currently experimenting without any issue so far. One customer feedback is highlighting that the temperature uniformity of the liquid allows to improve component lifetime and reduce failure rate. However, some components are kept at higher temperatures than initially planned. This is why we are still working on this and monitoring potential effects. Regarding power supply units, several points must be monitored in order to validate their compatibility and their ability to work within dielectric liquids. The electrical relay must be sealed. The capacitor must be chemically compliant. In the picture on the left, you can see a capacitor which inflated after immersion. This can sometimes go as far as tearing off the component. And the possible presence of thermal path in the power supply unit must be checked. Therefore, you have to check that the fan is perfectly disconnected and there is no fault signal. For this, you can, for example, use a fan simulator as you see in the central picture. Once all these points are perfectly under control, we test this power supply with a test bench specifically made for immersion. You can see it in the picture on the right. I share with you the physical tests we can do for the power supply units. It's also possible to make directly change in the firmware of the power supplies. It can be done directly upstream by the manufacturer, and you can deactivate the fan and prevent the fault signal, ensure weak ventilation for test in air, turn it off in immersion, and modify the over temperature protection to adapt to immersion if it's necessary. It depends on the constraints of the project. As a conclusion, immersion technology can be tricky. We have too many aspects to consider, test, and adjust for a dielectric liquid. The good news is once you master them, providing Immersion server is sustainable. We know that by taking the appropriate precaution, it's possible to transport the majority of air servers into immersion technology, which delivers significant advantages: money saving, component failure rate reduction, component life cycle increase, or IT densification. After 2 years of immersion experiences, SUSE RSI wanted to share learning and tips accumulated with the OCP community. We hope you enjoyed it. We are participating and will continue to participate in the OCP project Rack and Power Advanced Cooling Solution. You can find a lot of information on immersion and several practical guides with the link below. I invite you to join us on the Advanced Cooling Solutions section and to consult the documents written by many companies participating in the project. Thank you for your attention.